Okay, so with every conic section, we have a pretty intense definition. What you demonstrated with your dental floss ellipse, that is the definition of an ellipse. So you have 2 points, your brads. Okay? Every single point on your ellipse has the same sum of distances from those brads. Okay? So just don't write quite yet. Just look at me. Your dental floss never changed, correct? So when you add these 2 distances together, no matter where you are along your ellipse, the sum is going to be the same thing. Okay? Go ahead and write down what you need to, and then I have another image I want to show you. Okay, so a parabola has 1 focus, an ellipse has 2 foci. That's the plural for focus. An ellipse. So no matter what point you are on the ellipse, if you take the distances to the foci, they're going to add up to be the same thing. Okay? We demonstrated that with your dental floss. I'd like to give you another image if you just want to watch up here with me. Okay? Here I have an ellipse. I have this red distance to focus 1 and the blue distance to focus 2. Right here is the sum, 11.41. No matter where I am along the ellipse, that sum stays 11.41. Okay, so those 2, it's like my dental floss, right? Our dental floss changed shape, but its length always stayed the same. Those 2 distances always stayed the same. Okay, now if I have a different ellipse, here's one that's a little more circular. The distance changes, but stays constant as we go around the ellipse. Okay. All right. So, we have some vocabulary words that we need to take care of. Okay. I'd like you to draw this ellipse, and I want you to label. We have a major axis, we have a minor axis, we have a center, and we have 2 vertices. Can somebody tell me the difference between the major and the minor axis? Well?
Oh, shorter on the length.
Because I could turn it like this, right? Okay, so which one's longer?
Major,
The major axis is the longer one, okay? The major axis is the longer one. Minor, not as big a deal, is going to be the shorter one. Something else you'll want to keep in mind is that your foci will always be on the major axis. Okay, so you have these labeled up here, but focus and focus, those are on the major axis. Okay, so if we have a horizontal ellipse, our foci are horizontal from the center. If we have a vertical ellipse, our foci are vertical from the center. A lot of today is going to be getting used to the equations and this terminology: major axis, minor axis, center, focus. How do we find all these things from the equation? Okay, we're also going to get a little bit more practice at completing the square. Yay. Okay, I know some of you want some more practice with that. You'll get it each day. By the end of today, you're going to need to be able to walk out of here knowing how to graph an ellipse. If I give you an equation, can you put that ellipse on a graph for me? Okay? So, we have two types of ellipses, horizontal and vertical. Okay? This is what we call standard form. Okay, before you start writing, I want you to look up here very quickly. Don't write yet. Don't write yet. When we talked about parabolas, remember yesterday we really made it a point. One variable was squared, the other didn't have a square. Now, both variables have a squared term, okay? And we have addition in between. That's going to be important, okay? Proceed. Do you notice how you wrote that A is bigger than B? That's how you're going to identify if you have a horizontal or a vertical ellipse. Okay? A is the bigger of the two numbers. A is underneath the x squared, which is how we know it's horizontal. That'll become more clear when we look at the vertical one. Okay? So, in this ellipse, AB, what do they give us? Okay? HK is going to be the center. Okay? That sounds familiar. Okay? HK we use with parabolas as well. HK we're going to use when we get to hyperbolas on Monday. Okay? Whatever A is, that is going to tell you how far away those vertices are from the center. Okay? A will give you how far your vertices are from the center. B is going to give you how far away these, I'm going to call them minor vertices. Your book is not going to recognize them as anything, but they're important for our shape. So I'm going to call them minor vertices. But your minor axis you get by taking B from the center in both directions. Okay? Since this is a horizontal ellipse, we're longer horizontally than we are vertically. Okay? And then pretty soon I'll tell you about the number C. C is how we get the foci distance. Our foci are going to be C away from the center. Let's go ahead and write down the vertical ellipse equation. Very similar, with one and only one very big difference. Major difference. What is our major difference?
A and B.
Placement of A and B. Remember I said A is the bigger number. Well, now the bigger number, A squared, is underneath the Y, which is why it is a vertical ellipse. Y we associate with vertical movement. Our bigger denominator is now with Y. It's a vertical ellipse. I'm not going to take the time to draw the A, B, and C in this ellipse, but big difference here is we're going to use A vertically, since it's a vertical ellipse. We would use B horizontal, since that would be the minor axis. Okay. Also a major difference. Our major axis is vertical, so our foci are going to be vertical from the center. Your major vertices and foci will always be the orientation of your ellipse. A couple more things to talk about, and then we're going to do two examples. One example where I'm just going to give you the formula nice and pretty. One example where we are going to have to complete the square to get it into standard form. Okay. So go ahead and take a look at this picture for me. Okay, look at this picture. If we're talking about the major and minor axes, how long is the major axis? Okay, we move A away from the center in two different directions. So 2A would be the length from start to finish. Along those same lines, start to finish, for our minor axis, how long would that be? Our minor vertices are how far from the center? Okay, how far? B, so from start to finish, our minor axis would be 2B. Okay. We talked about this with our brads. What would happen if A and B were the same? We would have a circle. Okay. A circle would be a special type of an ellipse. Okay. Where A and B are the same, that was what we would call the radius. Okay. I would prove this to you, but I'd like to spend time on examples. C, this is how you find C. C squared is A squared minus B squared. Okay, so it's pretty similar to a formula you already know. You just have to change it a little bit. Okay, so C gives us how far our foci are away from the center. C can also give us a measure called eccentricity. Okay? Eccentricity tells us how ovalish our ellipse is. Okay? So eccentricity, we're going to take C divided by A. It's going to give us a number between 0 and 1. The closer that number is to 0, the more circle-ish our ellipse will be. The closer that number is to 1, the more ovalish our ellipse will be. Now, I know it seems like we've gone over a lot of information, and we have, but as long as we can have it in standard form, H and K are pretty easy to pick out, just like they were with a parabola. Once we identify A and B, it's just a matter of measuring from the sector, okay? So while yes, it looks like we've talked about a lot of information, it's going to come together real nicely, okay? Here we go. Don't write this down quite yet, because I'm going to put it in standard form for you. But here is a general conic equation. What do you notice about it? There's an x squared and a y squared, correct? So we know it's not a parabola. Because x squared and y squared have the same sign, in this case they're both positive, we know it is going to be an ellipse. Okay? Now, to save us some time, this is what I want you to write down. In standard form, this is x plus 3, the quantity squared over 4, plus y minus 1, the quantity squared over 1, equals 1.
Would it be given to us in standard form?
Sometimes yes, sometimes no. So we're going to do one where I give it to you in standard form, and one where I give it to you in that general form. So we can practice getting it into standard form. Okay, so the first thing I want us to recognize, is this horizontal or is this vertical? Look at the equation, turn to your neighbor, and tell them what you think. Okay, I heard a murmur of horizontal. Like we're getting tired or something. Okay, Jade, how do we know it's horizontal? Okay, our bigger denominator is associated with the x. That's great. Our center, we get by identifying HK. Colby, what's our center?
-3, 1.
Okay, -3, 1. There's our center. Now, we've identified that this is horizontal, which means a squared is underneath x. Okay? So a squared is 4. What does that mean about a? A is 2, because 2 squared is at 4. Okay? So, since we have a horizontal ellipse, and we've identified a to be 2, then horizontally we're going to move 2 away from the center for our vertices. Okay, so I plotted them and then I wrote down their coordinates. -3, -5, and -3, -1. The book is going to call them vertices. I'm going to call them major vertices because they're on the major axis. We're then going to go here to b squared. B squared is 1. That's nice, right? That means b is 1. So since this is a horizontal ellipse and b is 1, we're going to move in that other direction, vertically, 1. Yes?
We changed it.
Oh, I'm so sorry.
I was like, what?
I'm sorry.
Just saw that.
I was trying to,
Is the one.
I was trying to talk and write at the same time. You see me, that's weird. Okay, thank you for pointing that out. Don't be afraid to stop me. Okay? I knew I needed the -3 and the -5. I just put them in the wrong spot. Or the -1 and the -5. Okay. Now we identified B to be 1. So we went up and down 1 for our minor axis, and I'm just going to go ahead and label these as minor vertices. Okay. I think that they're important to label because they give us that nice shape. Okay. And so then we can connect the dots nice and smooth for our oval shape. Now, you wrote down a calculation for C, right? Robert, what was that? C squared equals A squared minus B squared. Okay. Well, we identified A squared to be 4 and B squared to be 1, which means C squared is 3. So C is radical 3. So our foci are going to be radical 3 away. I want you to leave it as radical 3. I know it's an irrational number, but we know radical 3 is roughly between which two numbers? 1 and 2. Radical 1 is 1, and radical 4 is 2. So we know that radical 3 has to be in between those two. All right, so we know that this is more than 1 less than 2. Okay, we don't have a lot of room on here. We just know we need to move right and left radical 3, and radical 3 is approximately 1 point something. Okay, so I'm going to do the best to plot the foci where they go. Okay, now let's think about this. We went from our center, -3, 1, and we went right radical 3. And we went from our center, -3, 1, and we went left radical 3. Since we have an irrational number, there's no choice but to write it like that. Okay. Now, for some of us, we think, that's a lot of writing, Mrs. Homan. If you have an irrational C, which more times than not you will, I have no problem with you writing -3 plus or minus radical 3, comma 1, and just clump them into one coordinate. Okay? But if your C value is 2, do not write -3 plus or minus 2. Okay, you giggle, right? But you know what -3 plus 2 and -3 minus 2 is. I would not want that, but if it's irrational, go ahead and clump them together, not a problem. Eccentricity is C over A, so C over A. Since that number is closer to 1 than it is to 0, a little bit more ovalish than it is solid. What do you think? A lot of prep work to get to that problem, but it really doesn't take too long. Okay, it's about the same amount of work as a prep work. Okay. All right, last example. Go ahead and write it down. Is this a parabola? It's a parabola?
No, no. It's the ellipse.
Okay, we have x squared and y squared present. Okay, so it's not a parabola, and since they're the same sign, in this case they're both positive, which they typically will be, then we know we have specifically an ellipse. Okay, if, like this was 9x squared and 9y squared, it would be a circle if those are the same, but since they're different, we know we'll have an ellipse shape. Okay, now, if we want to get it into standard form, we want it to look like this right here. It doesn't, which means we get to complete the square how many times? Twice. Once for x, once for y. Okay, so this is what we're going to do. We're going to group our x's together. We're going to group our y's together. And then we're going to throw that constant on the other side. Okay, all the constants get over to the other side. I'll show you why we need that here in a moment. Okay. Ooh. Can we complete the square with a coefficient that is not 1? No. Okay. So I got a little excited. I don't actually need those bars yet, but that's okay. We need to factor 9 out of this. So we have 9 times x squared plus 4x plus mystery number. Since this has a 4y squared, we need to factor out a 4. Left over is y squared minus 2y plus mystery number. Okay, so let's be careful here. X squared plus 4x plus blank. B is 4. B divided by 2 squared. Maddie, what completes our square here? 4. Okay. We are not going to add 4 to the other side. Why? This 4 is being multiplied to that 9. So we're really adding 36. Okay. Over here, 1 completes the square. B over 2 squared is 1. However, we factored out this 4. This one's really being multiplied to that 4. So we really added. So what we have is 9 times x plus 2, the quantity squared, plus 4 times y minus 1, the quantity squared, equals 36. We're still not there yet, though. In your standard form, what does the right side need to equal? It needs to equal 1. Our right side equals 36. So we can divide both sides by 36. So what we get, x plus 2, the quantity squared, over 4, because 9 over 36 would leave a 4 in the denominator, plus y minus 1 squared over 9, because 4 over 36 would leave us with a 9 in the denominator. From here it can be nice, right? As long as you can get to there, the rest won't seem so bad. Turn to your neighbor. Which direction does this ellipse open?
She's like, which one is it?
Tanner, which way does this open? And how do we know that? Okay, A is bigger than B, 9's bigger than 4, so since the bigger denominator is with the y, we open vertically. Michael, where's our center?
-2, 1.
We have a center of -2, 1. Great. Okay, now Tanner pointed out that 9 was the bigger denominator, which means that's the a squared. If 9 is a squared, what is a? 3. So what we're going to do, we have a vertical ellipse. We're going to move vertically 3 both directions from the center. By default, 4 is b squared, which means b is 2. So horizontally, we'll make our major axis 2 both ways from the center. Okay? And those are points I want you to label minor vertices. C squared is a squared minus b squared. So c squared is 9 minus 4, which means c is radical 5. I know that radical 4 is 2, which means radical 5 is just a smidgen bigger than 2. So when I plot my vertices, I'm going to plot them vertical because we have a vertical ellipse. And I know I just need to plot them a smidgen more than 2 away from the center. I took my center, -2, 1, and we moved up and down vertically, radical 5. Okay. What do you think? What? Oh, we could, yeah. If I asked for eccentricity, what would it be, Colby?
Radical 5 over.
Radical 5 over 3. Okay? Over the weekend, you're probably going to have to rely on your notes pretty heavily for this. The good news is, on Monday, we're going to learn about hyperbolas, and they're very, very similar to ellipses. And then when we work backwards on Tuesday, it's really going to enforce everything we know about ellipses and then hyperbolas. Okay? When's your quiz? Thursday. What am I doing with your quiz? Grading it with no corrections. I need you